Today we're going to talk about circles. We're going to start off with just some definitions and vocabulary that we can use when talking about circles. So first, what is a circle? A circle is the set of all points that are equidistant from some given point. Okay, so if I give you an arbitrary point and then I draw all the points that are the same distance away from that point, then I get a circle. Okay, this point right here, that from which everything is equidistant from, this is called the center. And the distance away that all the points are from the center is called the radius. Okay, we have the radius of a circle and we have the center. Concentric circles are circles that have the same center. And if they're also the same radius, then those are congruent circles. But a concentric circle, so it looks something like this, where we have a point, I have a circle here, and then I have another circle around it like this. Now I could have an infinite number of concentric circles and get this kind of bullseye shape. But these circles all share a center, they lie in the same plane, and therefore they are concentric. And if the radius were the same, right, then we'd only have we have basically two circles that are identical, so then they're congruent. A chord is a line segment that connects any 2 points on a circle. So if I have a circle and I draw a line segment that connects two of them, that is a chord. The longest chord is called the diameter, right? And the way we get the longest chord is I would draw it right through, if this is the center of the circle. And this is the longest chord I can have. And if the distance from the center to a point on the circle is r, the radius, then the length of the diameter is going to be twice the radius. Okay. Now, we can also think about how we know if I just take an arbitrary point and I want to know whether that point lies inside the circle, on the circle, or outside the circle. We can answer that question based on how it compares to the radius, right? So if I take a point, so let's say we have a point P, and I want to find where in or outside or on the circle it lies, then I'm going to find the distance from the center of the circle to P. So the distance from my point P to the center of my circle. Okay, I'm going to call that distance, we'll call it D1 to differentiate from the diameter. I'll make the diameter capital D, so there's no confusion around that. Okay, so then we'll just call the distance D, lowercase d. So if lowercase d is less than r, that means that my point has to be inside my circle, right? Since r is the distance from the center to where the circle actually is, if d is less than that, the point has to be inside. So if d is less than r, then p is inside the circle. If d is equal to r, then p is on the circle. Right, because then it's just right on the circle here. And if d is greater than r, then it's outside the circle. Okay. So now that we have all this vocab, I'm going to write down two equations you've probably seen before, which is the area of a circle is equal to pi r squared, and the circumference of a circle is equal to 2 pi r, right? So the area of the circle, we're talking about if I shade in all of this, how much area is there inside, pi r squared, where r is the radius, right? The distance from the center to the outside, and pi is the 3.14159, blah, blah, blah. The circumference is 2 times pi times the radius. The circumference is giving us the length of the outside of the circle. If I took this circle and unraveled it along a tape measure or a meter stick or a ruler, then how long would it be? And that's what the circumference is giving me. One last note to mention too is that, and this seems a little obvious, but just in case, if I have a chord like this and I want to find the distance from the center to this chord, we always use this perpendicular distance here. Okay, the line segment that connects the center to the chord here, this is if the distance from the center to the chord is the same as this line segment, which the book makes a very specific point of stating, but is pretty clear here. Okay, So now that we have our vocab, we're going to go through some theorems, some circle theorems. So the first theorem is that if a radius is perpendicular to a chord, then it bisects that chord. Okay, so if you draw a picture of this, you can kind of see why that is. I have my circle. So I have a chord. If my radius is going to bisect, is perpendicular to the chord, then it has to be right in the middle of it, right? Because if it wasn't right in the middle, then it wouldn't bisect it. If I drew it like this, then like all of a sudden this angle is not 90 degrees and it no longer bisects it. So when the angle is 90 degrees, it's going to bisect the chord and split it perfectly into two segments. So one more time, if we have a chord, if it bisects it, so these two are the same, and it's perpendicular. Number two is the exact same thing, but it's saying it works the other way. Where if instead I know that a radius bisects a chord, so if I'm given instead of being told that, hey, the radius is perpendicular to the chord, I'm told that it instead bisects that chord, so I'm told these are the same, then I can always assume that this is a right angle, right? For the same reason that we talked about up here. And then finally, number three, which is, again, very similar to number 1 and 2, the perpendicular bisector of a chord always passes through the center, not the radius. Sorry about that. I should say center. So what this means is if I'm told that I have a line segment like this that is a perpendicular bisector, so it's perpendicular and it bisects it, splits into two equal parts, then it must pass through the center. Okay. Because again, anytime you try to do something different, you can just see that it will not, right? If I have this is not a perpendicular bisector. Any perpendicular bisector has to go through the very center of the circle. Okay. So those are some circle theorems as well. So now let's go back to some example problems. So let's say I have a figure that looks like this. I have a circle. My center here is Q. I have a chord like this, where this point we'll call T. This will be S. And then I'm going to have a line segment that goes like this, and we'll call this point here R. And then I'm going to connect these into a triangle. I'm going to call this point P. Okay, here's what we're going to be given. In this problem, we're going to be given that the circle is centered at Q. So the way we write that is like this, Q. So our circle is centered at Q. We're also going to be given that the line segment PR is perpendicular to the line segment ST. Okay, so I know that this is a right angle. And what I want to prove is that line segment PS is congruent to line segment PT. Okay, so to do this, we're going to do a two-column proof. So what I'm going to do is I'm going to split this, and on the left side, I'm going to write my statements, and on the right side, I'm going to write the reasoning as to why those statements are true. So if I want to show that this line segment of PS is the same as this line segment of PT, these two-column proofs, usually where you're going to want to start is always with the givens. So my first step is just going to be to write down what the given is. And the given is that the circle is centered at Q, and also that line segment PR is perpendicular to line segment ST. And my reason for this is that it's given in the problem. Okay. And then I want to try to use some of my circle theorems. So what can I say? If I know that this segment here is perpendicular to this one, then I can also say that it bisects it, right? That it splits line segment ST in half. And I can say that because of circle theorem number 1, which we had in the last page. So I'm going to write that PR bisects ST, right? Because if something is perpendicular, then it has to bisect it, in this case with the radius and the chord. So my reason for this is theorem number 1. So from there, how can I now know that these two pieces are the same? Okay. So if I know that this line segment is perpendicular to ST, and it also bisects ST, that means that I can say that PR, line segment PR, is a perpendicular bisector of ST. And that's just the definition, right, of what a perpendicular bisector is. And then finally, what we can do is we can write the final statement. We can write that line segment PS has to be congruent to line segment PT. And why is that? Well, that is because if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints. And this isn't a specific theorem that we listed on the last page, but think about this for a second. So right here, right, I know that this splits, that point R splits segment ST in half. So SR is the same as RT, okay? Now if I take point R and I just move and I trace along the perpendicular bisector, the perpendicular bisector is going to, every point on it has to be the same distance from S and T, right? So if I go up here, this distance has to be the same as this distance. If I go up here, this distance has to be the same as this distance, right? And if I go all the way to point P, this distance has to be the same as this distance. So these two things are congruent, and we've completed our proof. You can also make an argument about triangles. If you've studied triangles before, you know that this angle and so these two angles are the same. You know this is congruent to this, and you know this side is the same. So then you can say that, oh, these triangles have to be congruent, so this has to be the same as that. So you can also make a triangle argument as well. Okay, let's look at another one. Let's say this time let's say I have a circle, and my circle point P and point Q, and it has a chord that connects them. And I'm going to have my center at O, and I'm going to say that the radius of this circle is 13 millimeters. I'm going to tell you that segment PQ, the length of it, is 10 millimeters. And I want to find the distance from segment PQ to O, to the center. Okay? So how do we do that? Well, I know that if I want to find this distance here, what else do I know? I know that this distance here is a radius, right? So if this is a radius, that means that segment PO is going to have a length of 13 millimeters. And then I also know that if I, because I'm drawing a line here, and I want to find this distance, this is a perpendicular bisector based on the circle theorems from the first page. So this is a right angle, and this is congruent to this. It splits it in half. And if that's true, that means that segment P to this intersection point here is going to be half of 10, so this is going to be 5. So then if I want the last side, I can just use the Pythagorean theorem. I can say 13 millimeters squared is equal to 5 millimeters squared plus x squared, where I'm solving for x and finding my distance. And if I do that, I find that the line segment from PQ to O, x is going to be equal to 12 millimeters. Okay. So note for this one, I didn't do a 2-column proof. To be fair, it didn't say to prove anything, so that's kind of why. Here it just said find the distance. So if it's just saying find the distance, then you don't have to do a 2-column proof. You can just work through the problem and figure it out. If it says prove it, that's when you're going to want to actually make statements and start with the givens, end with the prove, and use the two-column proof to fill in everything in between. Okay, good. And this distance, that comes from the last thing I said on the first page, which is that if you want the distance from the radius to the chord, then it's just the length of the line segment that connects the radius to the chord. So that's why we're able to get that. Okay, we'll do one final example, and we'll be done. So let's say for our last example, this will be another proof. It'll be a little bit of a longer one. Let's say I have two circles. I have a circle here. I have a circle here. This circle has a center at P. This circle has a center at Q. And let's say there's a triangle like this that goes up and connects these. And there's another triangle here. I'm going to call this point B. This point will be A, and this point will be C. Okay, so we're going to say that some stuff that's given in this problem, I'll give to you, is that triangle ABC is isosceles. So we're going to tell you that line segment AB, because it's isosceles, line segment AB is congruent to line segment AC. Okay, it's an isosceles triangle. I'm going to tell you that there's a center of a circle at P, and the other circle is centered at Q. I'm going to tell you that line segment BC is parallel to, this is the symbol for parallel to, line segment PQ. Okay, so lots of givens. And we want to prove that circle P is congruent to circle Q. Okay. So how do we set this up? Well, we are going to do a two-column proof, and we always like to start with our givens. Okay. So here we go. We're going to say, I guess I would do it like here. So statement 1 is just going to be what we're given in the problem. So I know that triangle ABC is isosceles, which means that line segment AB is congruent to line segment AC. And we know that because it's given. We have some more givens that we're going to put in here too. So our second given is that circle P is centered at P, and circle Q is centered at Q. And also that BC is parallel to PQ. This is also given. You can kind of put as many of these together on one line as you want. There's not like a standard thing you have to do, but it's nice to spread it out so one line isn't just packed with lots and lots and lots of stuff. Okay. So where can we go from here? Well, I can look at these angles, right? And I can say that angle ABC has to be the same as angle P, okay, or like APQ. And why can we say that? Well, we can say that because if you think back to when you studied parallel lines, you know that parallel lines, if two lines are parallel, they're going to have identical, congruent, complementary angles, right? So I'm going to say that angle ABC is congruent to angle P. And also, we can make the same argument here. We can say that, okay, these two things are the same, and also these two things are the same. And I can say, so that's angle ACB is congruent to angle Q. And that is all because parallel lines have complementary, they have congruent complementary angles. circles. Okay. 4. I'm going to say that angle ABC is identical to angle ACB. Why can I do that? Well, I can do that, right? So I'm saying that this angle is the same as this angle, and therefore, all these angles are the same. And I can do that because if I have a triangle, right, which has these two sides congruent, then that means that the triangle must have these two angles congruent, right? So that's just back from when you guys study triangles. For 5, I'm going to say angle P is the same as angle Q. And this is just the transitive property. Right, and the reason I can use the transitive property is because I know if this is equal to this, ABC is equal to ACB, but ABC is also equal to P. So I can put P in for ABC, I can put Q in for ACB, and they're equal. So that's transitive. 6, I can say that line segment AP is congruent to line segment AQ. So I'm looking at AP, this segment here, and AQ, this segment here. Why can I do that? Well, I can say that if a triangle has two angles like this that are identical, then I can say that the sides are identical, right? So kind of the opposite of number 4, just going the other direction. I should put it then in. So we just said, we showed that angle P was the same as angle Q. So now I'm allowed to say that AP is the same as AQ. So we're getting close to the end. So next I'm going to say that PB, line segment PB, is congruent to line segment CQ. So PB here, this little line segment, is the same as CQ in that side line segment. How can I do that? I can do it via subtraction. Right? I'm subtracting 1 from 6 because I know it's isosceles. So I know AB is the same as AC, and then from 6 I know AP is the same as AQ. So if AP minus AB has to be the same as AQ minus AC, which means that PB is equal to QC. Okay? And then we get to our proof statement. We say that circle P is congruent to circle Q. And the reason we can do that is circles with equal radii are congruent. This isn't really working. Congruent. Okay, so that's how we do it, right? You can kind of think of this proof and say, well, where are we trying to go, right? If I want to prove two circles are congruent, the way you do that is you show the two radii are congruent. So if I want to show the two radii are congruent, you can kind of almost work backwards. Say, well, I have to show that this line segment is the same as this line segment. So then how do I do that? Well, I'm given that this whole thing here is equal to this, and we then kind of work it out. So that's how you do a 2-column proof and how you use circle theorems to prove properties of circles. And that's it. So thanks for watching.